Hi, thank you. So I guess I can start. So hello everyone. My name is Yaniv Sar. I'm from Nokia Bell Labs. And in this talk, I'm going to be revisiting scalability and applicability of OpenStack placement. So since I think I'm short with time already, I'm going to start right into the outline of this talk. I'm going to start with a background on scheduling in OpenStack. And then the talk is a breakdown into two parts. In the first part, I'm going to discuss how to obtain an up-to-date state of the system. And then, if time will allow, I'm going to continue to the second part, which is service chain aware placement. In each part, I will discuss how OpenStack is doing it currently. And then I'll present an algorithm that is relevant to that part, and eventually I'll reach into an evaluation. All this work is backed up by published academic papers. If anyone is interested, I'll be happy to send references. Please contact me afterwards. So let's start with a schema diagram of typically how things are working. I should say that in this talk, I'll refer mainly to OpenStack, but this is also valid for any cloud system, provisioning of cloud system. So essentially, we have requests on the left-hand side that keeps arriving. And on the right-hand side, there is a set of compute, server, whatever you call them. And there is a central algorithm that needs to accommodate the placement request that keeps arriving to the system. This is essentially how things are working in cloud systems. So let's dive a bit into how things are working within the algorithm. There is fundamentally two steps that needs to be done. The first is querying the system resources and then filtering them based on whatever resource can accommodate the specific requests that have arrived. And then, after filtering non-relevant resources, there is a process of prioritizing the remaining resources. And then there is a selection to accommodate the requests that have arrived. So this is also a good place to say that the talk is breakdown into two parts. The first part will discuss about querying the system resources and filtering them. The second part will discuss the weighting resources and determining the allocation. So let's jump right into the first part of the talk. How things are being done in OpenStack? Well, there is the default OpenStack scheduler, which is the filter scheduler, which upon a request that arrives, fetches the system state, which is obviously when we have many computes and many servers, very networking intense, resulting in turn in a time-intense process. Time-intense process, of course, is problematic with respect to scaling the system. There are reports, we found several forums that discuss this issue, both in OpenStack and in Kubernetes, and there are many issues with scaling this query step. On the better side, at least this process has no false positives. False positive is relevant to the other solution that OpenStack has, which is the caching scheduler. In a second, I'll jump into it. So obviously, we have problems scaling this process. So one solution to this problem is the caching scheduler. The caching scheduler has this joint process that periodically fetch the entire system state, okay, which help us in scaling. We have now a controlled networking. We know exactly each period of time, each refresh step require a certain amount of networking. We have a control running time. We know exactly how much time will it take. And this is completely separated from the algorithm itself. The bad news about this, this variant of scheduler is that it depends on a stale state. Stale state meaning that it could be that what the algorithms see is not actually what is happening in the cloud. Now, an important issue about this stale state is that it depends on the refresh rate. There is a configurable refresh rate within OpenStack that enables you to set the period of time upon which we are performing the refresh of the cache. Now, what I'm going to show you now in the next evaluations, experiments that we have conducted, is that there is a problem right up front setting a single refresh rate. Whenever you set a refresh, there are cases where it won't work. You will have a poor performance with respect to quality of the placement. So, the message that I want to share, to convey in the following experiment slide is that there is no refresh rate that fits all. Then I'm going to present a solution that we have developed, which is rather simple, but answers all the problematic scenarios. And indeed, since there is no single refresh rate that fits all, this scheduler has become deprecated a couple of cycles ago, and now it's not supposed to be used, at least. So I should also say that there are many attempts, many variants of attempts, how to scale this approach, whether it is concurrent algorithms, whether it is breakdown of the cache, multi-cache, or breakdown of the state into several tiny open stacks. All of them are complementary to what we are going to present. It's not something that prevents one another. So let's first show an experiment where we want to measure the effect of caching on different placement heuristic. To do so, we implemented a simulation environment where we took a sequence of more than 4K requests of varying sizes. Requests could be VMs, by the way. I didn't say that. I assumed it's obvious. Could be VMs, could be VNFs, whatever job that keeps arriving. So the simulated environment takes a sequence of more than 4K requests of varying sizes, taken from running VNF system. We took enough compute to accommodate all requests offline. This is important because online it will have a certain decline ratio. And we took a varying refresh interval. So you can see in this experiment, we have 10, 50, and 100. And we also have always. Always is equivalent to the filter scheduler, meaning whenever a request arrives, I'm going to query the entire system and see what is going on in the system. So in this experiment, you can see that we compared several different placement heuristics. Actually, we did many more. This is the ones that we've chosen to show in this experiment. You can see distance from diag, which is a certain algorithm that tries to fill up hosts in the same proportion, meaning I don't want hosts to be fully occupied with their CPUs. I want them also to be in the same proportion with memory, for instance. So this is the first heuristic. The second one is BUP, which is balanced utilization placement, which is actually a multidimensional water fill. This is the default OpenStack heuristic. Then there is a first fit, which is the other heuristic that OpenStack implements, which is find the first fit, the first compute that can fully accommodate the request. This is called energy saving in OpenStack. And then there is a final heuristic that I've chosen to present to you, which is the adaptive approach, which tries to water fill up to a certain threshold, and then from a certain threshold, continues with the first fit approach. So the message that I wanted to show you in this experiment is that every heuristic behaves differently with respect to the refresh interval. So, for instance, let's have a look at the first fit. At the first fit, its behavior, when considering it with a caching scheduler, is problematic, because right after the refresh that is being done, few requests will be accommodated successfully, but then the following will think that the compute is available for grab, which is obviously wrong, and the decline ratio will have a poor performance. So I hope I convince you that different heuristics behave different with respect to the refresh interval. Following experiment is taking a set of different real workloads, taking from AWS and from Google. And what I wanted to show you in this experiment is that for AWS, the certain type of request that keeps arriving, their size, the size of the premise, the size of the cloud, the size of the server, result in, if you look at the 40-second refresh interval, all heuristic, whatever heuristic you'll take, will suffer from above 40% decline ratio. Whereas if you look at the Google workload request, even when you take 1,000-second refresh interval of the caching, most, at least not most, except from the first fit, which suffers the problem that I've described previously, will have less than 40% decline ratio. So in those two experiments, what I wanted to prove to you is that no one can find a single refresh rate that will accommodate all heuristic, that will perform good for any type of workload. So to begin with, this approach of caching the system is problematic. So this leads us to our suggestion of implementing an adaptive cache, a cache that dynamically knows how to change its refresh rate. Actually, it's a very simple algorithm. It's a very simple algorithm, and actually, if you ask me, this is the uniqueness of this approach. You don't need to implement a full-blown system that will monitor the current state of the system. You can do it very simply, just by having an adaptive refresh rate cache. And I will prove to you in the following experiment that it has the scalability of caching scheduler, the one which was deprecated in OpenStack. So it can scale. And on the other hand, it has quality as good as the filter scheduler, as if I was querying the entire system without actually really querying the entire system. So I'm getting the best of both worlds. So how is the algorithm working? Actually, this is a very simple algorithm, just monitoring the request issued during the last threshold interval t, then calculate the decline ratio that happened during the refresh interval t. Then, when the decline ratio is lower than a certain given predefined threshold, we are conservatively increasing the size of the refresh interval by 10%. On the other hand, when the decline ratio is greater than a predefined threshold, decrease the refresh rate by 50%. We are taking an aggressive approach, kind of like what's happening in TCP windowing. This is the basic idea. Very simple to implement. We implemented it in Nova, by the way, if I didn't say it. And now I'm going to jump into proving to you that we are gaining the best of both worlds. So we implemented Ask in Nova. For benchmarking, we utilized a GitHub project called OpenStack Benchmarking for scheduling. We needed that to emulate as many computes as we wanted. This project implements an emulation of compute. So what the algorithm thinks is that it have as many compute as I would like to. I could have 1,000, 10,000 computes without really needing the compute. It is only relevant to the algorithm itself. Okay? For this experiment, we took the caching scheduler that was deprecated and set the update rate to 60 seconds. As I was saying, of course, 60 seconds, this is what is given by default, but for a certain type of workload, it won't work. For a certain type of heuristic, it won't work. And for the experiment itself, what we did is issued, first, I'm going to show you that it is fast. The request throughput is high. Then I'm going to show you the quality. And so to do this experiment, we have issued a batch of 200 requests, measured the throughput by requests per second, and did it on a varying number of computes. Okay? So what you can see here is that ask is the green line, perform almost as good as the caching scheduler, even at times better, while the filter scheduler perform much worse the more hosts that we have. And why is that? And this is a simulated environment. And why is that? This is because the more hosts that you have, the filter scheduler needs to process many more computes, and it takes it much more time to process each request. So in this experiment, I hope I've proven to you that we are as good as far as scaling as the caching scheduler. On the other hand, we had another experiment showing that we are as good as quality-wise as the filter scheduler. And in this experiment, what we did is issued an ongoing randomly generated request. Each has a lifetime, but we have average lifetime is set to fill the computes nearly to reach the limit, because we want to see cases where there are OK declines, where there are true positive declines. It is perfectly OK. And we have a varying, again, number of computes. Please disregard the 600 compute for a second. I'm going to explain to you another issue in a second. But you can see here that ask, our implementation, is almost as good as the filter scheduler, while the caching scheduler obviously has issues knowing what's the current state of the system. So what's the issue that you see when we measured 600 compute? When we measured 600 compute, the filter scheduler has a spike. This is because the filter scheduler is choking, and it starts receiving many timeouts internally with the messaging. So at a certain point, it breaks down and starts performing even worse when comparing the decline ratio. So the first issue of throughput of scaling caused its decline ratio to perform poorly. So I think that I'm more or less done with the first part of the talk. So the takeaway that I would like you to take from this first part of the talk is that OpenStack default scheduler, the filter scheduler, does not scale to large clusters. On the other hand, caching enables to scale and make things faster, but it comes with a price of too many unnecessary declines due to stale state of the cache. Adaptive scheduling cache, which is the algorithm, the simple algorithm that I've just shown you, achieves placement quality that is similar to that of the filter scheduler, as if we know everything, but we are not asking everything. And on the other hand, faster with throughput that is similar to that of the caching scheduler. So this is the first part of the talk. Now I'm going to recall the algorithm, the process for scheduling. We started with a query, and I've presented to you an idea for an implementation for how to query properly. And now we are going to talk about the second part, which is how to perform the allocation. So assume now that we know everything about the system, and let's discuss for a second how to determine how to allocate each request. So let's look at an example. Again, we are assuming that we have a full and accurate view of the system. And on the left-hand side, now we have chains. What interests us is a service chain aware placement. Maybe I should have said that at the beginning, not just placement, but now we want a service chain aware placement. And on the right-hand side, you see a specific example of premise where we have 3 computes, A, B, C, with a certain capacity. Each has its own certain capacity. So the first chain arrives, and the default OpenStack implementation is to waterfill the premise. It tries to balance all the resources. This is at least the default. And then the green service chain also follows this same policy. But it is not clear, at least as far as service chain, what makes it better than the second policy that OpenStack has, which is energy saving, trying to pack as many requests as possible on as few servers as possible. Well, if you think about it, OpenStack policy refers to the premises, not to the request. It tries to optimize the resources, but nothing tries to optimize KPIs of the application itself. Okay? So, given a service chain, how should we place? So, we have several matrices. There is endless matrices, endless KPI that you can think of that you would like to optimize. And when we have only water fill and energy saving, the behavior is not relevant to the service chain itself. For instance, if you look at the hardware utilization, water fill is a good approach for balancing all the hardware. While as if, for instance, you have certain accelerators that are installed on a certain compute, maybe energy saving will be a better approach as far as the service chain goes. For networking, water fill increases the traffic between the computes, while as energy saving increases the traffic within the compute. So, and actually for switching, this leads me to switching. We have a separate work that we published that implements a prediction model that tries to predict how much CPU will it cost me to traffic a packet within a chain. Okay? This is a very important criteria because this is actually consuming resources from the computes. And usually people ignore it. Usually you are deploying a certain set of VNFs, of VMs, and you disregard the compute that it costs you to route the traffic between those VNFs. Again, this is a publication that we had. Sorry, 1 second. If anyone is interested, I'll be happy to share that later. So let's return to our example. And now, for instance, consider the case where you'd like to have low latency for the chain. Okay? So low latency means minimal hops. And then when you have the purple chain, you would like it to be as follows. You would like it to be separated spread between as few compute as possible that can accommodate the entire chain. This cannot be guaranteed by OpenStack in its current implementation, as far as I know at least. And I will show you in a second an algorithm that can deal with this requirement. Then let's have a look at the final chain, which is the red chain. And you can see here I mark it X2, meaning the first chain requires, for instance, a single CPU. The first VNF requires, for instance, a single CPU. The second VNF requires 2 CPUs, but OpenStack placement is not aware of the service as a chain. And what will happen is when the first VNF will arrive, it will occupy server C, and then you will have unnecessarily failure because you will not be able to accommodate the second VNF. So a better approach would have been if you knew right up front that you have this specific red service chain, would be to place it as follows. Again, OpenStack do not guarantee this behavior as well. It is not possible to guarantee that. And what we would like to have is an implementation, a placement algorithm that can a priori know how to place the entire chain and reject only if it is not possible whatsoever to place this chain. Let me do a time checkout for a second. Okay. So, what we implemented in this case is a placement algorithm that guarantees to reject if and only if placing is infeasible, which is important, and more important is to guarantee to find the optimal placement with respect to a given objective function. Now, you may ask, what is an objective function? An objective function is a cost that can be given to each and every compute. In fact, each compute could have its own objective function, whatever you'd like it to be. And it could be different between compute, whatever that you want to say about this compute, to give a cost for this compute. It could be the network traffic. It could be minimize hops. It could be hardware utilization, whether you have a certain accelerator or not. It could be a mixture. It could be lexicographically ordered between different KPIs that you'd like to optimize. And for a given objective function, we are guaranteeing to find the optimal placement. So how are we doing it? So let's first revise how OpenStack is doing it. Given a service chain with n VNFs, how should we deploy it over k servers? What policies should we follow? So Nova Scheduler ignores the chain, and per VNF queries all server as discussed in the first part of this talk, and then select a single one that can accommodate the placement. You can follow the global policy of either water filling or energy saving, but what I want you to note in this schematic placement is that n is very small, and OpenStack do not utilize it. And usually the size of the chain is very small. It's somewhere below 10. It's not something that is too big. So if you would have insisted to place the service chain in this premise, it would have taken you an order of k to the power of n, which is the classical bean packing. Okay? What OpenStack is actually doing in this case is just try once and then forget about it. I cannot accommodate, and that's it. But if you would have implemented through OpenStack a way that will guarantee to find a placement if it exists, it would have cost you order of k to the power of m. Again, I'll remind you that n is very small. N is very small. So why not utilize this fact by searching the combination of what the service chain could be break into the servers. So let's focus on iterating all possible decomposition of the chain. Colors here represent designated servers that is going to be found to accommodate this sub-chain. Okay? And all possible decomposition is captured by Bell numbers. Bell numbers are order of n to the power of n, iterations, it means. And for each iteration, we are reducing the problem to bipartite matching and to mean cost flow, which is, you can see the polynomial on the right-hand side, which is order to n to the power 3, k to the power 2, plus ta-ta-ta. And this we are doing n to the power of n iterations. Again, this is not simple, but there is another relaxing factor that you can use in order to optimize it, which is usually chain goes into a server at most once. If it goes at most once, it's either in a server, in a compute, or not. It cannot go back and forth. And in this example, you see cases where, for instance, the blue subchain is entering the blue server and then going to the red server and back to the blue server. This usually is not happening. And if you use this fact, if you utilize this fact, you are getting a slightly different problem, which is decomposing of integer composition. This is called a known problem called integer composition, which is n to the power of n, 2 to the power of n, which means that we have 2 to the power of n iteration of following the reduction for the problem from bipartite matching to mean cost flow, etc. So now we have order of n to the power of n iteration, 2 to the power of n iteration of this nice polynomial for the reduction. So the algorithm is rather simple. What it is doing is starting from infinite cost and iterate over all decomposition, whether it is the optimal case or not, or the relaxing case. And then for each partition, builds a bipartite reduction, which, as I shown you, is a simple polynomial. If it is indeed the minimal, it tries to follow the minimal cost. If it is indeed the minimal, then update the result. So some evaluation. Again, this is a simulated environment where we evaluated the case where we want to guarantee that a placement is done if and only if, placement is rejected if and only if it is not possible to accommodate the service chain. And as you can see, Nova Scheduler quickly, this is a log scale time access. And as you can see, right from the third or fourth chain size, OpenStack cannot accommodate such a request, while as the optimal can grow into chains of size 5 or 6, and with the relaxing assumption, the OCM algorithm can scale easily to up to 10, up to chains of size 10, which is easily a couple of seconds of going through all iteration and then performing the reduction. So let me go back to summarize what I have shown. So we said that placement is made of 2 fundamental steps. The first one is querying the system resources and filtering them. For this, we've shown you that adaptive scheduling cache, a new technique, can dramatically improve the way we are scanning the entire system. And for the second part, where we weight the resources and determine the allocation, we have shown you an optimized service chain aware placement, OCM. And I actually skipped, I can show you I prefer to stop here, so I think this is it. Thank you. Questions? Yeah.
What release of OpenStack were you using to test this out?
We needed to take an old OpenStack Mitaka because we needed a project that implements the benching. Yes. Yeah.
So you haven't looked at anything with the placement service? The actual, it's called placement?
Again, I didn't understand.
There's a new service.
Yeah, I'm aware of it. It's with etcds. What? No.
It's API, that's not etcd.
Okay. No, so I'm not familiar with that. No.
What you're calling placement
Mhm.
is what we generally call scheduling.
Yes. I'm sorry.
And so there's a new service that we call placement
Uh-huh.
that is designed to solve a lot of the issues that you're talking, not the service chain, but all the
Okay.
querying thing. There's no false positives.
Uh-huh.
And it means the filter scheduler doesn't try to digest the large numbers of host states that were kind of the basis of the problem.
But as I was saying, there are many. I'm not very familiar with the cutting edge of what OpenStack is currently doing. But there are many, as I was saying in one of the slides, there are many possible ways to relax the problem of scaling. But essentially, whatever you'll do, I think that this slide was referring to this issue, not issue, to these solutions. Whatever you'll do, you'll eventually get into the same problems. Whatever, I'm not sure how your placement is currently implemented, and I think that at least what I presented here is complementary to whatever solution are currently available in OpenStack.
That's actually a shared state scheduler.
Again?
That's a shared state scheduler.
Okay. Okay, yes.
That helps you to actually scale out.
Mm-hmm.
Because this is stateless. So you basically just have to run as many placement API services as you want.
Mm-hmm.
We could probably refer to the SunV2 presentation that was made yesterday when they explained how they actually try to scale with Sales V2 and the new placement API. Because, I mean, I'm just trying to explain that the problem that you mentioned
Mm-hmm.
was indeed a real problem with Mitaka, and that was the reason why
What
there
it
was
will.
such benchmark. Because at the time we discussed,
Mm-hmm.
we were discussing about the new design that we are going to take after Mitaka, and the answer to that specific benchmark
Mm-hmm.
was the placement API, which is a shared state scheduler with a single commit. And to be honest, have you actually identified the allocation situation that we are? I mean, just if you're running Mitaka, when a commit is made on a specific request,
Mm-hmm.
this is made on the compute, right?
Okay.
So that's one of the reasons why we had search problems.
Mm-hmm.
And that's also why, since Okata, we just modify that because no, the scheduler makes atomic commits.
Mm-hmm.
So, I mean,
I still think it's orthogonal, but I think, but again, I must say, I don't want to. I'm coming from academic point of view, but the little engineering that I do know, solutions that are too hard to implement and too difficult to implement are usually not. I'm sorry to. I hope I'm not barging into, but usually are not the right solution for the long run.
that's the exact reason why I said this is a shared state scheduler with single commit,
Mm-hmm.
with generation bits.
Okay.
Because that kind of algorithm has been had some academic publications showing that in case of scalability, this can be the way to solve the problems.
Which is, what is this? The solution?
Shared state scheduler.
Searches. Sure. Well, it could be. It could be. But I think that at least engineering-wise, I'm sure that this solution that I've shown you is by far simpler to any other implementation. But again, and I honestly think that it is completely complementary to each other. It's not that one way that you implement it prevents it from doing it this way as well. But
So I was going to ask, are you amenable to proposing this code upstream? And no?
I'm not, I don't care helping whoever would like to, but I'm not into implementing it in OpenStack, so it's not.
I mean, I guess I'm asking
No, it's not. No, actually, it is publicly available, published. It's academically published, so you can implement whatever you'd like. It's not something that is proprietary to Nokia.
I was wondering for the service chains, how were you able to correlate like a group of separate requests as being part of one chain?
Again, this is an academic work. The technicality of how am I offering an API for the user within OpenStack is not part of our work. We didn't do it. It's not something that is implemented in OpenStack, this part of gathering the chain. Time is up, but questions are welcome. You can come approach me. Thank you.